If we can follow the complexity of biochemistry back to well beyond when our sun was forming, that means that there's a chemistry that's consistent across our galaxy, or in our galaxy, that would say we didn't have just the only conditions in the entire galaxy to form life. We had the same biochemistry that's got a heritage all the way back to well beyond when the solar system formed.
The hope was that by collecting particles directly from a comet, one, we know what comet, we know absolutely we have particles from a comet, we know which comet, and we know information about that comet from astronomical observations.
What was surprising is that they confirmed that it has an extremely anomalous isotopic signature, which means that it definitely has an interstellar heritage.
What we're finding are dust grains that formed in these outflows of stars. Their isotope compositions reflect these nuclear reactions that occurred in their parent stars. These dust grains floated around in space for some period of time, possibly as long as 1 billion years, before they just happened to be caught up in this cloud that collapsed to form the solar system. These are example isotopic images collected of stardust sample with the nanosims downstairs, but the pumps aren't so loud here. What you can see is this little particle here that seems to be kind of Pac-Man shaped is much, much more enriched in nitrogen-15 than this particle. But it turns out both of these particles have anomalous abundances of nitrogen-15. These are carbonaceous materials. This is some of this organic matter that's part of the comet that might have been formed in interstellar space. By studying the carbonaceous materials in these, we get a handle on what the original form of the carbon was that hit the Earth, that was delivered to the Earth, and that eventually turned into us and everything else organic on the surface of the Earth. So, to some extent, things like this are our, ancestors, chemically speaking.